In this video, I will be discussing topic 12b, entropy and energetics. So this is continuing from 12a, and I have divided topic 12b into part 1 and part 2 because part 1 I'll be discussing more about lattice enthalpy, and in part 2 I'll be discussing more about solubilities. Okay, so let's start. We're going to start off by giving the definitions for some of the concepts. We have standard enthalpy change of atomization, and this is the symbol, the delta sign, and the atomization at and then H for enthalpy. Enthalpy change when 1 mole of gaseous atoms are formed from its elements in their standard states under standard conditions. So we have the 1 mole of gaseous atom of chlorine gaseous atoms formed, and those are formed from the elements in their standard states, right? So chlorine is a diatomic molecule, so it exists as Cl covalently bonded to another chlorine atom, but it's still gas, so the state symbol doesn't really change. Okay, so we need half of this molecule because we only need to form 1 gaseous chlorine atoms. Okay, now the next one is the electron affinity. So this is the enthalpy change when 1 mole of gaseous atoms gain 1 mole of electrons to form 1 mole of negative ions. So over here we have the chloride mononegative ion, which is gaseous, and we have the chlorine gaseous atoms, electron being gained by this guy, so we get the chloride ions. Oh, I forgot, to form 1 mole of negative there should be a gaseous over here, so the ions must be gaseous. Okay, now the next definition, lattice energy or lattice enthalpy. Enthalpy, this is the enthalpy change when 1 mole of an ionic lattice is formed from its gaseous ions under standard conditions. So over here we have the sodium chloride and magnesium chloride as our ionic lattices, and we have the gaseous ions that form the ionic lattice over here. So sodium ions and chloride ions. Over here we have the magnesium ion. We have 2 chloride ions over here, right? Because the ratio between Mg and Cl in a magnesium chloride ionic lattice is 1 to 2. Okay, so we're going to try and construct a Born-Haber cycle. And here we have the Born-Haber cycle for NaCl as our ionic lattice. So from this energy level to this energy level, the difference is that over here we have the elements in their standard states, right? And we're going to form the ionic lattice. So this is going to be the formation probably. And over here, on the very top, we have the gaseous sodium ion, we have an electron, and we have chlorine. Gaseous atoms, and then over here we have the ions, and so this is probably going to be the electron affinity. And as we go down, the difference is going to be, we have gaseous ions over here, and the lattice enthalpy definition was forming 1 mole of an ionic compound from its gaseous ions, right? Yeah, the gaseous ions over here, and this is the ionic compound, so this is obviously going to be the lattice enthalpy over here. And from this level to this level, the difference is going to be, so we have Na gas, that's not different, right? If we look at the chlorine though, from here we have the half a molecule of chlorine, this, and over here we only have the isolated gaseous chlorine atom. So this is probably going to be the atomization, right? And from the, this level to this level, that is going to be the atomization of sodium, right? Because the changing thing over here is that the sodium solid becomes gaseous, right? And the definition for atomization is making 1 mole of gaseous atoms from its elements in their standard states, okay? And lastly, this arrow over here will be representing the first ionization enthalpy for sodium, right? Because sodium is losing an electron. We're stripping away an electron from sodium to make a sodium ion, okay? 1 positive sodium ion. Now, I have labeled all the enthalpy changes over here, so if you want to note it down, you can pause and note this down. You kind of have to know how to construct the Born-Haber cycles and to know which one is missing, basically. But we'll look at a example question. So we're going to try and construct the Born-Haber cycle of MgCl2. Okay, so first of all, this arrow going down here from this level, we're going to have to make this first of all, right? So this is probably going to be the delta FH, and over here we're going to have the elements, Mg solid plus, over here we don't have to do a half molecule of chlorine because we need to, so Cl2 gas, okay? And yeah, so if we're going up, first of all, I'm going to atomize my magnesium, so it's going to be Mg gas, not solid anymore, and chlorine just goes up. And then, so this is atomization of Mg gas. And when I'm going up to this level, I'm going to atomize my chlorine atoms. So Mg gas plus 2, this is for this arrow, plus 2 Cl gas. So we have 2 atoms of chlorine. So that from here to here is going to be delta atomization H of Cl2 gas. Over here, actually, it has to be half, and we have to times this by 2 because now we're making 2 gaseous atoms of chlorine. And from here to here, I'm going to have to ionize Mg to make Mg2 plus the gaseous ions. So therefore, over here, it's going to be the first ionization enthalpy and the second ionization enthalpy as well, because we're stripping away 2 electrons. So one first, so that's the first ionization enthalpy, and then the second would be the second ionization enthalpy. So I'm going to have 2 electrons that has been stripped away, and I'm going to have the chlorine gaseous atoms. Now, the chlorine gaseous atom has to gain those electrons to become ions, okay, chloride ions. So that's going to be Mg2 plus gas plus 2Cl minus gas, so that it became ions, chloride ions. So that this arrow is going to be the EA, electron affinity of chlorine gas, but we need to times this by 2, right? So over here, the difference between the sodium chloride was, first of all, we didn't have to do a half over here because we kind of need the 2 atoms, right? And we had to times the atomization enthalpy of chlorine times by 2 because we need 2 moles of gaseous chlorine atoms. And also we had to do first and second ionization enthalpy because Mg has a 2 plus charge, not a plus, just 1 positive charge. And we also multiplied the chlorine electron affinity by 2 as well, because we have to ionize, we need to make 2 chloride ions, okay? All right, let's try and look at an example question. So over here, identify the missing detail represented by the following letters. So first of all, I have delta Z, okay? And delta Z, I know that it's the formation enthalpy for barium oxide because I'm going from the elements in their standard states to the ionic lattice. So we're forming the ionic lattice from elements in their standard state. That's why it's going to be our enthalpy change of formation. And we have the next is delta W. Delta W, let's see the differences between the start and finish of the arrow. The start over here, we have the barium 2 plus gas and oxygen gas, and I just added the electrons because the electron has to be removed from barium to make the barium ions. Sorry. Yeah, and over here we have the oxide gaseous ions now over here because the oxygen has gained one of the electrons. So W has to be the first electron affinity of oxygen gas. Yeah, the difference over here is that oxygen gas, this is just the gaseous atom of oxygen. Over here we have O- gas, right? So one of the electrons has gone into oxygen. So that's the electron affinity. And we have R as our last mysterious letter. We have barium 2 plus gas, and over here on the arrow we can see that it's a second electron affinity for O- gas, right? So we must have O2 minus gas, which means that it gained one more electron. Okay, so yeah, second electron affinity of oxygen gas. All right, the next says, use the following data to calculate the value for the quantity of delta Z shown in the Born-Haber cycle. Include a sign and units in your answer. So over here, the enthalpy changes are all given. The numerical values of enthalpy changes are all given. So I have labeled the Born-Haber cycle with all the data over here. I recommend you do this in your actual exams so that it's easier to write down the calculations. So we have to work out delta Z, right? And so the starting point over here, that's the start, and this is the finish, right? Yeah, that's the start and the finish. And so we basically have to take the long way around, so the direction. So the purple line over here, this is the direction to which the reaction occurs, okay? So we have to basically follow along all the arrows that I colored in yellow. So therefore, we're just going to add up basically all of these values. So 180, 503, and then on and on and on and on. And then you should get 499.9 kilojoules per mole as your delta Z, which is the formation enthalpy for barium oxide. Okay. Oh, by the way, I did not put any negative signs in front of any of these values because the arrows are all going parallel to the direction to which the reaction occurs. Okay, if they go in opposite directions, obviously the signs must flip, meaning that you should put the negative signs in front of these values. Okay. Right, and the table gives some information about the lattice energies of barium oxide and magnesium iodide and shows the percentage difference between the theoretical and experimental values. So we have the experimental and theoretical lattice energy values, and we have the percentage differences. So barium oxide is 0.8 and magnesium iodide has 16.5. Explain why there is closer agreement for barium oxide than for magnesium iodide. So before we look at the specific barium oxide and magnesium iodide, the difference between the theoretical and experimental data for lattice energies is due to the covalent character. Okay, so when a cation, which has a high charge density and is very polarizing, polarizes an anion's electron cloud, the partial overlap of electrons between the nuclei occurs. So as you can see in this diagram, we have the little partial overlap between the nuclei over here, right? Because the cation has polarized this electron cloud of the anion. So there's a larger percentage difference for magnesium iodide than barium oxide, as you can see from the data given. This indicates that magnesium iodide has significant covalent character, okay? But whereas barium oxide is almost 100% ionic, okay? Because of the very similar experimental and theoretical lattice energies, okay? So I just drew the diagram for magnesium iodide and barium oxide. So the Mg2+'s ionic radius is smaller than barium 2+, while having the same charges, right? They all have 2+. Therefore, magnesium ions, magnesium ion has a higher charge density, right? It's more polarizing. Yeah. So that is the cationic contribution to the polarization, and we have the anionic contribution as well. So also, iodide's electron cloud is much larger, and basically the electrons are far away from the nucleus than the oxide ion O2 minus. O2 minus is very small, so it's very tightly bound. Therefore, the iodide ion is a lot easier to polarize, okay? So that's why magnesium iodide has significant covalent character, whereas barium oxide is almost 100% ionic, okay? Yeah, the higher the covalent character, the higher the percentage difference between the theoretical and experimental lattice energies, okay? This is the concept that you must remember. Yeah, and so we're gonna just explore their reasons why to this. So theoretical lattice energies are calculated based on an assumption that ions in an ionic lattice are point charges. So basically the plus charge is basically just like a point, and the negative charge is also a point. Okay, so they don't occupy any volume. But ions have electron clouds, right? So electron clouds are going to look like that. That's for a covalent molecule, but more accurately it's like this. So that would be an ion, this would be another ion, right? So therefore they're not point charges. But experimental lattice energies are true values that take into account covalency, but theoretical lattice energies don't, because the assumption is point charges, okay? So that's why there is a difference between them, okay? That is why differences occur, okay? So that was part 1 to this video. Thank you for listening, and I'll see you on part 2.